Yes, Yashuvardhan, did you have any question, beta?
Sir, from HC1.
As you have a doubt? Yeah, just send me the question number.
Yes, sir, one second.
Yeah. Okay, I'll take a look at this question. No, yes, continuous mass distribution does not necessarily mean that the distribution of mass has to be non-uniform. We can have a uniform distribution also. But in yesterday's example, we specifically saw a non-uniform distribution so that we made use of integration. Is the question in context of that, like the example we did yesterday? Okay. Yeah, so the reason why I demonstrated the integration method with the non-uniform example is because instead, if we had taken a uniform thin rod, then we already know that the center of mass is at the midpoint. So there's no need to use integration. You got the point now? So yeah. And yes, you guys will send the recording and notes just now. Jitesh, the questions you have sent are from which chapter of H.C. Verma? Center of mass or circular
Center
mass?
of mass.
Center of mass. Okay, I'll take a look at those questions. Okay. So let's just get started with a little bit more of integration examples first. Okay, so we saw that for continuous mass systems, we use this formula for position of center of mass. It becomes, instead of integration, instead of summation, it becomes integration of R into dm divided by the total mass. So this is the general formula. Now the guidelines that we follow, that if the system is a linear distribution, so this is center of mass of a continuous distribution of mass. Now further we saw that if the distribution of mass is linear, then we take dm as a linear element. If it is a surface, then we take dm as a surface element. And if it is a volume distribution, then we take it as a volume element, like this. Okay. So we were looking at an example of the application of this for a linear distribution. So let's look at another example to start with today. So next example we will see is center of mass of a semicircular arc. Okay, so in this case, just imagine a thin uniform wire, okay, is bent into a semicircular arc shape. Okay. So where would the center of mass be? Okay, so the system we are looking at here, now something like this. Or basically another way to visualize this would be that imagine we had a circular ring kind of thing made of a thin wire, and we just cut it into half. So we're left with a semi-ring. Now we want to find the position of the center of mass of the semi-ring.
Yes,
So
sir.
one thing we can see about this system is that if we draw the axis that bisects it, the axis that passes through the center of curvature and bisects the 180-degree angle that the arc makes, then that axis is a symmetry axis, right?
Yes,
हाँ
sir.
The center of mass will definitely lie on the symmetry axis. Okay, so it's really about calculating one coordinate of the center of mass, and that is, if I take this as the y-axis, the vertical one, and I just want to find the y coordinate of the center of mass. The x coordinate I already know is 0. Okay. So if O is the center of curvature and this is bisecting it, then I know that the center of mass will lie somewhere here. Okay, so I just have to find the y coordinate of the center of mass. So to find the y coordinate of the center of mass, I will once again use that formula. Okay, r is the radius, suppose. Okay, so I need to, so what I've understood here is that the y-axis is the symmetry axis, because it bisects the semi-ring. So either side is like a mirror image of the other side. Okay, so it's a symmetry axis. You can fold it about itself and it will perfectly fit, that kind of thing you can think. So it bisects the semi-ring, and the origin O is the center of curvature. It's not the center of mass, but it is the center of curvature of the semi-ring. So because the y-axis is the axis of symmetry. Yes, very good, Jitesh. Okay. So now we need to understand that the center of mass lies on the y-axis. Okay. So at a point, let's say 0, y cm, that is the coordinate. So we need to now find out the y coordinate of the center of mass. And for that, we'll use this integration. Okay. So basically, again, this is coming from this. So from this, you can see that the y coordinate will be integration y dm divided by total mass. So now it's a matter of calculating this integration. Okay. So for this integration, you can see that here, again, mass is linearly distributed. Okay, over thin wire. So the mass is how much? It is m, and it is uniformly distributed over a wire of length pi r. Okay. So that is the answer for a semi-disc. Okay, this is for a semi-ring. We'll see the answer will be something little different. Okay. Anyhow, so let's work out the integration. Okay. So wire का length कितना होगा? वो pi r होगा, because it's in the shape of a semi-ring. So what is the so the lambda of the wire will be how much? It will be total mass divided by total length.
m upon pi r.
Yes, sir.
Yes, pi r. Okay. So our dm should be lambda dl. Okay. Now the thing is how we select the dl. So dl is like a small section of the semi-wire, no? Semicircular ring. So small section here will be like a small arc.
Yes.
A differential arc.
Yes, sir.
So when we cut a differential arc, we can see that we will follow the guidelines that we did for circular motion. Though there's no circular motion here, but we are on a circular arc. So we will identify any point on the circle. Yes, so now the answer is correct. Okay. So we will identify any point on the circle by what? We'll identify it by its angular position. We'll use the concept of angular position that we had seen in circular motion. So we will slice an arc somewhere here. Okay, so that we'll understand that we can locate that tiny arc or that tiny particle of length dl from its angular position with respect to the x-axis. So this is how we locate this small section. Okay. So this section, if its length is dl, then this is also subtending a small angle d theta. So that length of that section should become a radius into angle. So dl, as you can see, is r d theta. So this is how we locate a differential arc length on a circular ring. So dl is a differential section of the wire. Okay. And that differential section of the wire itself is actually a very small arc. So that differential section, it's a arc, and it subtends a differential angle d theta at the center. Hence its length becomes r d theta. Okay. So the mass of that differential particle will become lambda into r d theta, and lambda we've already seen is total mass upon pi r. So you can see, and dm, which is lambda dl, will become m upon pi r into r d theta. So m by pi d theta. So we have in the integration, now we can see that we will substitute dm in the above integral as m by pi d theta. So if we substitute dm as m by pi d theta in this integral, then what is a variable of integration? A variable of integration is going to be theta, no? Because we have replaced dm in terms of d theta. Okay, so that means we have to express y also in terms of theta. Right, so we are expressing y in terms of theta. That means, back to this diagram, we have to find the y coordinate of this differential particle over here. To find the y coordinate of this particle, but in terms of what? In terms of theta. So what is going to be the y coordinate of this particle? It's going to be this. This here is going to be the y coordinate. No?
Yes, r sin.
Yes, so it's r sin theta. Similarly, if I wanted to find the x coordinate of that particle, it would have been r cos theta. But I already know that the x coordinate of center of mass is 0, so I don't really need x. Okay. You can also understand by symmetry why the x coordinate will be 0, because for every particle on this side, there is another particle exactly on the other side at a symmetrical 180 minus theta kind of position. So that one and this one together are a symmetry pair, jinka center of mass kahan pe? Y axis pe. So that's why the whole system center of mass will lie on the y axis, right? So now I can see that the y coordinate of that particle, okay, so that dl element, its length is actually r d theta, its mass is therefore m by pi d theta, and its position x comma y is such that y is equal to r sin theta, okay, just as x is equal to r cos theta. Okay, so we will use this information for this integration now. So back to the integration part. So the whole system center of mass is at integration y dm. So y I am replacing with r sin theta into dm, which I'll replace with m upon pi d theta, okay, divided by mass. Now what should be the limits over here? Upper limit and lower limit kitna hona chahiye?
0 to 1.
Sir, 0 to pi.
Yes, very good, because we are integrating for all the particles right from this one here, let's say, right up to this one here. So at this point, what is the value of theta? It's 0. And by the time we reach the diametric opposite point, we reach pi or 180 degrees. So the limits of integration in radians will be 0 to pi. Okay. So now take the constants outside. So mr by pi is a constant. So we are left with a very simple integration sine theta from 0 to pi. Okay. And there's of course a division by m, so that m will cancel off. And then sine theta from 0 to pi, if you put the limits, will give you 2. So many of you got this answer correctly. It will be 2r by pi. Okay. Now having done this derivation, now we will commit this to memory as a standard formula. Okay, we will have to keep in mind this example as a standard formula so that we can apply it in problems. Okay, so integration of sine theta is minus cos theta, and when we put the limits 0 to pi, you can see that you will get 2. So this will be, so what this is finally telling us is that if we have that semi ring, okay, then the center of mass of the semi ring lies at a distance of 2r by pi from the geometrical center, but on the symmetry axis. This is the information that we are getting from this, that given the semi ring, this is the symmetry axis and this is the geometrical center. So the center of mass will be at such a point that this distance between the center of mass and this, that is 2r by pi, okay, where r is the radius. So this is the final result, which, as I told you, we have to keep in mind as a standard formula also for JEE level questions. Okay, so I'll just
Center of mass will lie close to the arc, right?
it is somewhere between the arc and the center of curvature. Yeah, so 2r by pi, if you see now, yes, it is above the midpoint, you know,
Yeah.
because it is r by pi is greater than half. And
Yes.
pi is 3.14 now, so r by pi is greater than half. So yes, you are correct in that it lies closer to the edge of the arc than to the center of curvature O. That means it's above the midpoint of that vertical line. Okay, so just make a quick review of this, then we will move on to some more such examples. We'll also come to those H.C. Verma example questions very soon.
Done, sir.
Okay, so hope all of you understood the
Yes, sir.
whole process. Okay, the geometry of the situation, how we made use of the symmetry axis. Okay, then also
Sir, do we have to remember this integration wala thing, like
Yeah,
The
remember the integration wala thing means like, see, the integration part is the full derivation. No? So you have to know
like
the process. You have to know how to do it. You don't have to
yeah,
memorize the
process.
steps. But the result is what you have to memorize. You have to remember directly that the center of mass of a semi-ring is at 2r by pi.
Yes, sir.
Okay, and I'll show you for which type of questions also you have to remember this. Okay, because there will be questions where you have to make an application of this. So that is only part of the question. So you don't have that much time to sit and derive this in the exam. Especially, JEE Advanced, more tricky type of questions. So actually, whether you're talking about JEE Mains or Advanced, if you are coming across a situation where you have to make use of the center of mass of a semi-ring, you must know the result directly. You will not have enough time in the exam to derive it. That's why I'm saying this is one of the standard examples you should. Okay, now we will look at a variation formula of this. Variation in the sense that it's not necessary that we are always dealing with a semi-arc. Okay, so we could be dealing with any general arc which is subtending any angle. The angle could range from anything from 0 to, 0 is the trivial case, but greater than 0 to up to 360 degrees. So one thing we know is that if it's 360 degrees, then of course the center will be at the geometrical center. But what about any angle in between? Okay, so suppose it's subtending, let's say 150 degrees, or it's subtending 200 degrees, or it's subtending 120 degrees or something. So how to find that out? So center of mass of a thin uniform arc. So subtending an angle alpha and of radius capital R. So just generalizing that result now. So instead of cutting it into an exact half circle, suppose we have sliced it such that it's like this movie. So join it with the center of curvature, which is, say, maybe over here. You can see that it's subtending some angle which is more generic. Okay, so then we have to again do a similar integration. Okay. So once again, the line that bisects the angle it subtends, that will be the axis of symmetry.
Yes, sir.
Sir.
So now what we are saying is that this point O is the center of curvature. This radius is R, and this angle we have taken to be alpha, this whole angle.
Yes.
So there is a line that passes through the point O and bisects this angle, and that particular line will become the axis of symmetry. So once again, the center of mass will lie on that axis of symmetry.
Yes,
So this
sir.
time, so again, we have to take that particular line, the angular bisector of alpha, drawn from the center of curvature O. We have to take that as one of our axes. So generally, because it looks like the vertical axis here, so I'll take that as the vertical y-axis. Okay, and once again, we can see that y-axis is an axis of symmetry, whereas in this case, x-axis would not be anything very significant here, other than the fact that it's just perpendicular to the y-axis. Okay. So this is our x-axis. So once again, now we know that the center of mass will lie somewhere here. Okay. So we want to find the y coordinate of the center of mass. So it's a very similar process. Okay. So y-axis, which is the angular bisector at the center of curvature O, is the symmetry axis. Hence, once again, the center of mass lies on it. And once again, integration r dm divided by, integration y dm divided by total mass. So the entire process is the same, but the difference will be what? How is
So
this
the
going to be
limits-
different?
limits.
Yeah.
The limits of the
Yes.
integration and even the angle which will be denominator after
Yes.
integration.
The limits will become different. Okay. So what we'll have to do here is if I take, and once again, the angular position with respect to x-axis. I can always take the angular position with respect to y-axis also, but I'm just going by the same method. So I'll take the angular position with respect to x-axis. So if I do that, then what is going to happen is that I'm slicing a thin arc at some theta like this, okay, and that's subtending d theta at the center and all that. Okay. So this y coordinate of the particle is again the same. It's r sine theta only.
Yes.
So I'm taking that dl equal to r d theta. Therefore dm. Now dm यहाँ पे क्या हो जाएगा? Lambda dl. Lambda will change. Lambda कितना होगा अभी?
So m by alpha r.
R alpha. No, because the total length of the wire is having mass m. It will have a length of
R
R
alpha.
alpha, because
Yes.
alpha is arc length upon radius. So make use of this. Okay. So ये हो जाएगा m upon r alpha into r d theta. Okay, so that is m by alpha d theta. Okay, and the y coordinate of that is again at r sine theta. So all these things now I have to substitute here. But after substitution, also another difference will be, like you said, the limit. So r sine theta into m upon alpha d theta. But this will go from theta equal to this point. So this point has an alpha equal to how much? Sorry, theta equal to how much? Alpha by 2, correct?
Yes.
Is it? Or is it 90
Like
minus
90
alpha?
minus alpha by 2.
Very good. It's pi by 2 minus alpha by 2. So this point will have, let's say this point is A and this point is B. So at the point A, the value of theta is equal to 90 minus alpha by 2. And at the point B, the value of theta is how much?
90
Pi
plus
by
alpha.
alpha. Pi plus alpha by 2.
Either way.
Yes, I know. This is going from A to B. So pi by 2 minus alpha by 2. Pi by 2 plus alpha by 2. Okay. So complete all these steps, and another standard formula for us to remember, this will become, now the easy way to remember this formula is that it is again r into sine alpha by 2 divided by alpha by 2. So actually when you work it out, it will come out to be 2r sine alpha by 2 upon alpha by 2, but I've written it this way. Okay. And you can see that the semi-ring case is the special case of this. So from here you can see that the other formula was one of the applications of this formula. For alpha equal to pi, we take a semi-ring. So our alpha by 2 is pi by 2. So YCM will become 2r by pi.
Yes.
We'll get this. But also if you take another type of case, for example, if I take alpha is equal to pi by 2, that is a quarter circular arc. So if it's a quarter arc, then the y coordinate of the center of mass, you will see, will become this sine alpha by 2 will become 1 by root 2, and alpha by 2 in the denominator will become pi by 4. So it will be 2 root 2 r by pi. Okay, so that means if I have this kind of a shape, I have a quarter circular arc. Let me draw that properly. Yeah, so if I have a quarter arc like this, then that one will be subtending an angle of pi by 2 at the center. of curvature. So this angle is pi by 2. So its center of mass will lie on this 45-degree line, and that will be at a point such that OC will be equal to this angle is equal to this angle, pi by 4. Okay, so just make a note of this also. And like I said, the derivation is for your understanding process and for to learn more applications of integration. But this is also another standard formula that you should memorize. General position of center of mass of a circular arc. It is at a distance of r sine alpha by 2 divided by alpha by 2. And in this thing, keep one thing in mind, that you always substitute alpha in radians in the denominator. When you substitute alpha, it should not be in degrees, it should be in radians.
Yes, sir.
Done, sir.
One.
So, yeah, all the steps are clear.
Yes, sir.
Yes, sir.
Just a second.
Yes, sir.
Okay, done. Good.
Yes.
Okay. Now, next we will look at an example of a surface distribution. Now, so far we have seen linear distributions. So as the first example of surface distribution, so first we'll cover all the standard cases. So this one is another standard case. So it's going to be another standard formula which we'll develop, which you will memorize. Okay. So this one is a semi-disk, a thin uniform but semi-disk. Okay. So center of mass of a thin uniform semi-disk. Okay. So this time it's that kind of situation. We have taken a disk which has uniform mass distribution. That means the mass per unit area on the surface is uniform, but then we have sliced the disk into half exactly. Okay, making it a semi-disk. Okay, and then we have to find the position of the center of mass. So it's a surface distribution of mass, unlike the cases we were looking at earlier, which were all linear distribution so far. So let's say this semi-disk's mass is only m, okay, and its radius is r. So once again, it has this axis of symmetry, and the center of mass will lie on that axis of symmetry. So once again, the symmetry axis. Okay, hence the center of mass will lie at some position like this, where we have to calculate this by integration y dm divided by total mass. Okay. Now, additionally here, dm should be what kind of element?
Sigma D.
It should be a sigma dA type of element because this is a surface distribution. So obviously sigma is mass per unit area. So that will be total mass divided by pi r square by 2.
Yes, sir. 2 and 5.
Now the question is, what should we take dA as? What kind of, how should we slice the disk, okay, into smaller areas, or how should we slice the semi disk into areas so that we can take the differential
into a
area?
small radius here, maybe.
So
So we
one
can
very
divide
convenient
by-
option that we have is we just found out the center of mass of a semi ring. No?
Yes, sir.
So we can slice the disk into semi rings. The ring's radius is increasing from 0 to capital R. And
Yes,
then we can make use of the formula that we just did. That's one option. Another option that we can do is we can slice it horizontally into thin lines, thin little rods, which are parallel to the x-axis. We can do that also, no?
yes.
Yes.
Okay, so both the options are there. So we will do in the class one of the methods, and I will give you the guidelines of how to try out the other method. So you can try that yourself later. So we'll take the method of the semi rings, okay, because in a sense that's the most standard kind of method. But you can always slice it into thin rods also. So now this surface, now imagine on this surface I'm slicing a thin semi ring like this. So this semi ring that I've sliced, imaginary slicing that I've done, okay, this one has a radius, let's say, which is some variable. So we can take it as x, or in this case, I'll take it as small r, and its own thickness is dr. So we'll take what we call a differential semi ring. Differential because its own thickness is very small. Okay, so its radius is r and thickness is dr. So now can you tell me how much should its area be? How will we write the area of this thin ring, semi ring? Yes.
Just a second.
So, you know, you can visualize that thin semi ring like as if you've taken a rod of length L and thickness dr.
So pi dr square minus pi r square. It's
That's
small.
also one option. Or another simpler option is that just think that you have taken like a ribbon, no, of length L, and then you bent it into a semi ring.
Yes, so that's
Okay, so then the length of that semi ribbon, I mean, a semi ring, that ribbon's length would be how much? It would be pi r.
yes. Sir.
So the area can be taken as length into thickness, isn't it? So here the
Yes.
area will become how much? It will become pi r into dr.
Pi r into
Pi r.
dr.
Into like this. Or like you were saying, you can also express the area as the area of like a outer semi disk r plus dr whole square minus, I mean,
Yeah.
minus
Pi r.
By 2. Okay. Now in this, when we do the calculation, we will neglect the dr square term because dr is very small, so its whole square is tending to 0. You following my point?
Yes.
So if you take pi by 2 common here, you have this r plus dr whole square minus r square. So if you open this term, it is 2r dr plus dr square. So this term is negligible. It's tending to 0. So this will become pi by 2 into 2r dr. So that's another way of understanding why that area should be. Okay, but the easy way to quickly, you know, just write it without too much calculation and all that is just imagine you open this semi ring straight out. So it's become like a linear rod or a ribbon like that, which you opened out of length L and thickness dr, and that length should be exactly equal to pi r, because when you fold it like this, it's fitting into that semi-ring shape. So that's how the area is becoming like this. Okay. Now the next thing, the y coordinate of the center of mass of the system. So what about the y of this? So this is the differential semi-ring. Okay, we'll come to y coordinate. It's first, let's write its mass. So its mass is sigma into dA. So sigma was 2m upon pi r square, and dA we just saw is pi r dr. So the mass of that semi-ring is equal to 2m upon capital R square into r dr. Okay, this is the mass. Now coming back to the integral, I'll substitute dm as this. Okay, but what should I substitute y as? So you can see the variable of integration is going to be small r. So I have to express the y coordinate of that semi-ring center of mass. Okay, so this semi-ring center of mass is lying where? At 2r by pi.
Yes.
Yes, sir.
So this C over here is the center of mass, but not of the disk. It is the center of mass of dm, which is the semi-ring. Okay, the thin semi-ring. Okay, so that we know it is at y equal to 2r by pi from the previous derivation. So we'll make use of this. Okay, so now for the whole semi-disk, we have to just integrate this term and divide it by the total mass. So substitute this, and put the proper limits. We are taking the entire semi-disk. So small r should range from where to where? From 0 to capital R.
Yes, sir.
Right. So the smallest semi-ring will be like a dot at the origin, and the largest one will be the circumference of the semi-disk. So it will be at capital R. So put that range of values and see what you're getting for the y coordinate of the center of mass. So just complete the integration and send me the answers. Yes, correct. Vedant and Jitesh, your answers are correct. Okay, just a minute. I'll share the whiteboard again. The answer should be 4 times capital R by 3 pi. Okay, just check. You should be getting that from the integration. Yes. Just a minute. I will share the widescreen board again. Okay. Right. So let's look at the final steps of the integration. Right. So this will become, we substitute here. So this will become integration of 2r by pi into 2m by capital R square, r dr from 0 to capital R, the whole thing divided by m. So 4m upon pi r square comes out. We're left with the integration of r square dr from 0 to capital R. So this becomes 4 upon pi r square to r cube by 3 from 0 to capital R. So that you can see will give you 4 r by 3 pi after putting the limits and everything. So having done this integration now, again, this is a standard formula which you have to memorize. Okay. Okay, so this is an example of a surface distribution. Now, like I was telling you, alternately, we can also use the horizontal differential strips as the elements for integration. Instead of this method, you can also do this. You can slice the disk into thin horizontal rods like this. So if we do that, let's say at a distance y, you've sliced a rod whose thickness is dy, okay, and this length here is x. So the total length of that rod is actually 2x. So the area of that thin rod will become 2x into dy. Okay. So the mass of that will become sigma into dA. Sigma is the same as above. Okay. Now in this you can see that x square plus y square is equal to r square. So you'll have to use the fact that x is equal to root of r square minus y square. You have to substitute this over here and do the integration. So the y coordinate of the center of mass, it become integration y dm divided by total mass. So the y coordinate you let it be because the rod center of mass is at this y only. Okay, so that will be this into sigma into that dA, which is 2x dy. So further, when you substitute x over there, so this will go from y equal to 0 to y equal to r. So in this x, you will have to substitute like this. Okay, and sigma you will have to substitute as 2m upon pi r square and complete this integration and all that. So on doing that, this will give you the same result. Okay, so you can try this later. This is the alternate method. And take dm as thin like strips parallel to x-axis. Okay, very good, Jitesh. Hmm.
So this YCM equal to 4R divided by 3 pi. So this
Yes.
formula is for which type of C1 means?
Which type of COM means this is the center of mass of the semi-disk. No? So the center of mass of the semi-disk will lie on this line only, the bisector, but from the origin or from the center of curvature, it will lie at a point which is that much distance. No? Understood? No?
But sir,
This
when
dis-
we found the formula, the 2r by pi, it was the same, right?
No, that was a semi-ring beta, and this is semi-disk. It's different distribution of mass. No?
Okay, sir, got it.
Understood the point? No?
Yes.
There the mass was distributed just over this length of that semi-ring. It's a thin wire or a thin rod which you bent like that. Okay. And this is a surface. No? You cut a disc into exactly half.
Okay, sir, got it.
Okay. So now we move on to our first example of a volume mass distribution. We'll do this example, and with that we'll have seen examples of integrations of all three types: linear distribution, surface, and volume. Okay. Then we can move on to something else, including some questions and things. Okay. So let's look at an example for volume distribution, and for that we will look at this case of the solid cone. Solid cone of uniform density. So the mass distribution is uniform. Okay. So it's also that symmetrical type of cone where the line joining the apex of the cone with the center of the base is the vertical axis of the base, that kind of cone.
So you mean the right circular cone, right?
Yes, correct. Right circular cone. Okay. The technical name for that in geometry or mathematics is right circular cone. All right. So this one center of mass, if you try to just figure out, estimate, you'll realize one thing, that the center of mass definitely lies on the vertical axis again. But as in terms of where it should be on the vertical axis, should it be above the midpoint or below the midpoint in my diagram? Because the vertex is above.
Below the midpoint.
Below.
It should
Below
be
the
below,
midpoint.
because it is heavier at the bottom. If it had been at the midpoint, then it should have been a solid cylinder. Okay. Or the density could have been variable, whatever be the case. Okay. So again, I'm taking y-axis as the symmetry axis, which is passing through the apex and the center of the base. So the base is, let's say, the disc or circle that lies in the in the xz plane. So the origin is exactly the center of the base. It's the centroid of that circle. So it's the z-axis. Okay. So once again, we can see that the center of mass will have to be somewhere over here. So it's all about finding the y coordinate of the center of mass. So y cm we have to figure out, because the center of mass will lie at 0, y cm, 0. Again, we have taken y-axis as the symmetry axis. The origin as the center of the base, the disk of the base. Okay. And this lies in the in the xz plane. So let's say the base radius is r and the vertical height of the cone is h. Now we're going to see something very interesting in this, that when we finally get the result, the y coordinate of the center of mass surprisingly does not depend on the radius of the base. It only depends on the height. So that's something that at least I would think is not that intuitive. Okay. Because what that means to say is that if I have two different cones of the same height, so I have a cone which is fairly thin like this, narrow. So it has some radius r1, okay, but a height h. And now I compare this with a much wider cone. but that wider cone is having the same height h. So R2 is greater than R1. So what the result will show us is that both of them are having the center of mass at the same height. So this doesn't seem so obvious, at least not to me. But anyway, the calculation will show us that. Okay, so we'll find the y coordinate of the center of mass by using this formula again. But this time, what kind of element should be dm?
So like multiple circular discs from
Yeah. But first of all, it should be a volume element because it's a volume distribution. It's a solid cone. Okay. So it's a volume distribution. So it's a volume element. Okay. And now, yes, we will think about like how to take dv. So how should we take dv? The most convenient would be to slice the cone using a plane which is parallel to the xz plane. And if you just slice it like this, like
yes.
So we will get those thin discs, like you were saying. We'll get thin discs. All those discs are having that common axis, which is the y-axis. Okay. But as you go up, the discs are becoming of smaller and smaller radius.
Yes.
And therefore, if you compare these discs, they are becoming smaller and smaller in mass, till the last one at the top becomes almost like a particle of negligible mass. So such a disc is of radius, let's say small r, okay, and thickness dy, because that thickness is along the y-axis. Okay, so this volume element that we'll take will be a thin disc, okay, sliced by a plane parallel to the xz plane. So this thin disc is of radius small r and thickness dy. So what about its volume? Its volume will become pi r square dy. Okay. Now in the other thing in the formula, what should be rho? It should be mass upon volume of the cone.
Yes.
Okay. Can you tell me what is the formula of volume of cone?
Pi r square h by 3.
Yes, 1 by 3 pi r square h. So this being the case, now we can see that rho dv will become 3m upon r square h. Pi cancels out into r square dy. Okay, so from this formula, it's pretty obvious that we are going to use y as the variable of integration. So we'll have to write small r in terms of y. So I'm coming to that also, but I'll need some space to just note down this part first, then I can scroll down. Okay.
Yes, sir. Done.
Answer copy.
Now, to make this little bit more manageable, what we will do is now, no, Vedant, you will see the answer has to be in terms of h, not in terms of h square. But yeah, anyway, let's quickly figure out. Yes, Jitesh, that is correct. Okay, now what we'll do is now, instead of taking the position of that disk from the base, we will take the position of the disk from the apex. So we'll just reverse our axis. Okay, the advantage of doing that is that we can then relate that distance very easily. I'll just show you what I'm trying to say. Yeah, so यहाँ पे क्या करेंगे ना, instead of locating the disk from the origin which is at the base, we will locate the position of the disk from here, from this apex point. Okay, so from this point, if the disk is at a depth of, let's say, y, it's just like a negative y coordinate basically. Yes, okay. Then between y and r there is a relation, which is the same thing as the relation between this whole depth, which is h, and this base, which is capital R. See, these two triangles are similar. This triangle and this triangle. This is small r, this is capital R. This is y. This whole depth is h. So we have that relation that y by r will be equal to h by capital R. So we can substitute y as h by r, both of which are constants, into small r. But now here y is not the distance of the disk from the base. Y is the distance of the disk from the apex. It's the disk's center with respect to the apex P. So when we use this formula for the above derivation, we will get the distance of the center of mass from the apex, not from the base. So YCM is, when we use this here, the YCM we will get is the center of mass of the cone, but it is going to be with respect to the apex T, because we have done this referencing. Okay, so now let's substitute. So actually we'll substitute the reverse, not this, because we want to get rid of small r. The integration is with respect to y. Now you can see that is in terms of dy. So I've just written this in reverse order. We will substitute small r as capital R by h times y. This is the substitution we will do, okay, in this. So once we substitute this, dm, which is rho dv, will become 3m upon capital R square h into r by h into y whole square into dy. So that becomes, your r square will cancel out, right, in the denominator. So we will have 3m y squared dy divided by h cube. Okay, so far?
Yes.
Okay, so now we substitute this here. Okay, so this becomes y dm, and dm is 3m by h cube into y squared dy. Okay, and this is going from y equal to 0 to y equal to h, the whole thing divided by m. Okay, so now we are in a position to simply complete this integration. So YCM, take all the constants outside, 3m upon h cube comes outside. Okay, we are left with the integration of y cube dy from 0 to h divided by capital M. So capital M also cancels out. Okay. And y to the power 4 by 4 from 0 to h. So the y coordinate of the center of mass with respect to the apex will come out to be 3 by 4 h. Or you can say that y center of mass with respect to base be h by 4. And as I was telling you earlier, might be somewhat surprising that the position of the center of mass does not depend on the radius. It only depends on the height. So therefore, whether we have a thick one or a thin one, the center of mass will be at the same 1/4 of the height from the base, or 3/4 of the height from the apex. Like this. Okay.
Done, sir.
One.
Sir,
Okay, is the calculation clear, everyone?
Yes.
Okay. There is also a different situation of a hollow conical shell. Okay, that has a different position of center of mass. That is at h by 3 from the base. But that is a surface distribution, and this is a solid cone. Okay, so naturally a solid cone has the center of mass at a lower position compared to the hollow conical shell. And so that's why this one is h by 4 and that one, if you compare, is h by 3. So we will discuss that also at some stage. Okay.
So will
But
we then take rings instead? Discs?
yeah, in the case of the hollow surface like that, no? For example, we'll also take an example of a hemispherical shell, like a hemispherical bowl, or the
Yes.
case of a conical shell, like an open conical shell. In both the cases, we will slice it similarly using a plane parallel to the exact plane. But when we slice it, instead of getting solid discs, we will get rings.
Yes.
Okay, so we will see that technique of integration also later, and that we will add to our example set. Okay. Acha, so this is clear, this example. Now I'm moving on to a couple of questions from HC Verma, which Jitesh you have asked. Yes.
Sir, can you just explain that that By-Shome is 3h by 4? That is for which one? Means this
That is
center.
from the apex beta. Because see, this has come from this integration. No? So in this integration, what we have taken y as over here. This result, no? This result has come from this integration actually. No?
Yes,
So
sir.
in this integration, remember what was small y? It was the distance of the ring of the disk from the apex.
Yes, sir.
So therefore, the reference was which point? The point P, not the point O below. So that is why this is the position of center of mass from the apex point P. And that is why when you take it from the base, this becomes the position. It becomes h by 4. Okay, from the center of the base. Got it, no?
Yes, sir. Got it.
Okay, good. Right. So now, as I said, I'm moving on to some questions with application type of examples. So I will start with HC Verma center of mass chapter. Question is that Jitesh has asked number 30 and 36. So you have HC Verma, please turn to the main exercise of system of particles. Otherwise, I'm just going to refer to the question here also, so don't worry. Just give me a moment. System of particles. Okay, so let's look at question 30. Okay, so it's talking about a cart, a luxury cart drawn by horses. The wooden plate is fixed on the rear, on which one person can sit. Okay, and this kind of cart or buggy is of mass 200 kg itself, and it is moving at a speed of 10 kilometers per hour. It is overtaken by a schoolboy, or rather, it overtakes a schoolboy walking at 4 kilometers per hour. And the boy sits on the wooden plate. Okay. So let me try and explain what this question is trying to suggest. Okay. Right. So Now we have to imagine that we are in a very ideal situation, frictionless kind of surface, and there is this wooden platform. So this is driven by horses and all that. So I'm really going to struggle to draw a horse. So I'm not going to do that. Okay. So this is moving at 10 kilometers per hour. Okay. And this has a mass of, what was it given? 200 kgs. So actually we'll modify the question a little bit, because the thing is now, if it's being driven by a horse, then can't really do momentum conservation, because the horse might provide momentum by applying additional force. So anyway, there is this boy who's traveling at a speed of 4 kilometers per hour. And as the plank sort of overtakes him, he climbs onto the plank.
Yes, sir.
And his mass is 25 kg. As the mass of the plank is like this. The plank is moving at a speed of this. Okay. Next moment, what happens is that the boy climbs onto the plank. And what we have to assume in the question, which is not actually explained, is that while the boy is climbing onto the plank, the horse does not apply any additional force on the plank. Okay. Because without that, the question would not make sense. And the surface below is also frictionless. So now this starts moving as a system with some common velocity v. Okay. Now while the boy climbs onto the plank, it's CB question number 30. So while the boy of mass m2 equal to 25 kg climbs onto the cart, which is of mass 200 kg. So during that event, assume no additional force is applied by the horse on it. So then we can do momentum conservation. So therefore, taking the boy plus the cart as a system, we can see
Sir, I got the answer.
External force will be 0. So yes, so conservation of linear momentum. So this thing that this assumption that we have done, it's not very obvious from the question actually. It's a bit of guesswork that we have to do, that how we'll solve the question, right? So we have to do it this way. So conservation of linear momentum will tell me m1 v1 plus m2 v2 initially should become the total mass of the system moving with a common velocity v.
Yes.
So just substitute and you'll get the value of v from this. M1, M2, v1, v2 you substitute from my diagram above.
It will come as 2100 upon 225 after.
Yeah, something like that. So when you substitute, so understood the concept now?
Sir.
Okay. Okay, so just write this down. Now let's move on to question 36 next. So just read through question 36 after you finish with this review. And the thing is, in a question like this, you need not convert to CGS units or SI units, as long as you're consistent with the units on both sides. Okay. So I have taken mass in kgs on both sides and speed in kilometers per hour in both sides. So there's no problem. Okay. I don't need to convert kilometers per hour into kgs, into meters per second, because I've taken consistently on both sides. So the units cancel in that sense, and whatever V I'll get over here, that will be in kilometers per hour only.
Yeah.
Okay. So that's one thing. Okay, now let's go through question 36. So question 36 is, so again, a block is moving at a given speed. It collides head-on with another block of equal mass kept at rest. Okay, so this is a collision-based problem. Okay, I will explain to you how to solve these kind of problems in some time. Okay.
Yeah. So actually, I've done the 30th one. 35th one.
Okay. So this question, you will need a hint on how to solve it, because we haven't discussed the concept of elastic and inelastic collisions yet.
Yeah.
Okay. And the definition of coefficient of restitution. So
Yes,
the
sir.
second part, leave it out for now. Okay, I will explain coefficient of restitution in the next lecture actually. But first
Yes.
part, I will give you a hint and we can try and solve it now only. Okay. So the hint is that when two objects collide, the maximum loss of kinetic energy will happen in the collision if the objects stick together.
Yes, sir.
Okay. So, you know, a typical kind of situation where, let's say, you have a sticky object moving on a frictionless surface and it goes and hits a stationary object, but as it hits it, it sticks to that stationary object.
Like
Hmm.
it becomes a system and it
So
carries
they,
forward.
yeah, they become a combined mass, which then have that momentum which the initial sticky object
Then
had.
they will move with a common velocity, right?
Then they will move at a common velocity. So when that kind of situation happens, there is a maximum possible loss of kinetic energy. Whereas if they don't stick together, then the first object might rebound if it is lighter, or the second object might run away with a much higher speed if that is the lighter one. So in that situation, there is comparatively less amount of loss of kinetic energy.
So like the elastic collision which you were
Okay,
saying.
yeah. It may be perfectly elastic, it may not be perfectly elastic. Perfectly elastic means zero loss of kinetic
Yes,
energy.
that's the ideal case. Yes.
But that, no. Whereas we call the situation where the two objects stick together as the inelastic collision. Okay.
Yes, sir.
So in an inelastic collision, the two colliding objects will stick together and become one combined object. And in that situation, only the loss of kinetic energy is maximum.
Yes,
So,
sir. Yeah, got it.
so using this, you will be able to solve this. Okay. So of course, definitions of and all of these things I will be coming to in detail in collisions when we discuss about collisions. Okay. So now let's look at another type of question. Moving on. Just a second. Okay. Now next we'll look at a question using the principle of superposition for center of mass, like we had discussed earlier. But now we will have to utilize some of the formulae that we have seen today for that one. So we'll start with this example. This type of question is also there as a direct numerical in HC Verma. We'll see how we can use the principle of superposition. So it's like we have a thick ring instead of a thin ring. We have a thick but flat kind of. Okay. Or you can even think of it like we first cut the disc into a semi-disc and then further cut out a smaller semi-disc from it. Okay. So this is the mass part now. So it's like we had a semi-disc of some radius R2, let's say. Okay. And then from that we cut out a semi-disc of radius R1. So this is it. Okay. So now given that R1 is equal to 4 centimeters, R2 is equal to 6 centimeters. Okay. And this is a flat surface of uniform sigma, that is mass per unit area. So we have to find the position of the center of mass with respect to the center of curvature. Okay, so the center of mass, as you might guess, will be somewhere here. It might be inside, might be outside, I don't know, but it will be somewhere on this y-axis.
Yes.
So find the position of the center of mass with respect to that geometrical center of curvature of the two curves. Okay, just try this out. So you can go with an integration method also, slicing it into semi rings and all that. But since you already know the formula of center of mass of a semi disk, you can better avoid integration and make use of the principle of superposition, the similar kind of principle we were discussing yesterday. Let me explain what I mean by using superposition principle. Yes, that will not be the answer. That's correct. Okay, so the principle that I can use here is one formula that I know, that if I have a full semi-disk, if I had this full semi-disk instead of one with another smaller one cut out, if I had this of radius R2, okay, where would its center of mass be?
8 by pi.
It would be at
8 by pi, yes, sir.
4R2 by 3 pi. इस पे होता,
Yes. Yes, sir.
Now I also know that the portion that I'm cutting out, so let's say this full disk is of mass m, a semi disk is of mass m, so this one center of mass would be at this. Okay, now the portion that I'm going to cut out from that, if I look at that portion separately, so let's say this is the mass m1 which I have cut out, and this mass, this part has a radius r1, so where would this one center of mass be? C1. C1 would be at y1 equal to 4r1 by 3 pi. Okay, so now the unknown mass that I'm trying to find out, I mean the unknown center of mass, that is this body's. So let's say this body's mass is m2, okay, and its center of mass is at some position C2, which I don't know. So its center of mass is, let's say, somewhere here, where this y2 I don't know. But I know that if I superimpose this and this, then I get this. So what I know is that if I superimpose m1 and m2 in my diagram, then I will get m,
Yes, sir.
which is the one on the left. Okay, so that is a superposition I will use. That superposition of these two masses m1 and m2 will give me the mass m, which I have over here. Okay, so what I'll do is now I will replace the same origin as this one, same origin as this one. I will replace the whole semi-disk m1 with an equivalent particle m1 at the position C1. Okay, and I'll replace the whole cut semi-disk m2 with an equivalent particle at this. So this system center of mass should be where? This system center of mass should be here, where this C is this known quantity. This C is this one.
Yes.
So I have m1 y1 plus m2 y2 divided by m1 plus m2.
Yes, sir.
That should be y. It's yc. So now the differences in this equation, we don't know y2. We know y1 and ycm. Y2 is what we have to find out. Okay, y2 is what we have to calculate. Y1 is something we know, and ycm is something we know. Okay, but in the meantime, we also have to figure out m1 and m2. So m1 and m2 kaise aayega? M is some sigma into pi r2 square by 2. Okay, so it is sigma pi by 2 into, now r2 was how much? 6 centimeters, no?
Yes, sir.
Yes, sir.
Okay, so it is 6 centimeters square. Okay, what will be m1? You can see in the diagram above, it is pi r1 square by 2.
Yes, sir.
Okay, and r1 was 4 centimeter. And what is m2? It is m minus m1, no?
Yes, sir.
So you can see that if we write this as 36 times something, then this is 16 times that.
Yes, sir.
Yes.
Okay, so this will become 36 minus 16, or it will become 20x. Okay, so I can replace, where x is just this sigma pi by 2 term only. So we can replace these masses like this.
Yes, sir.
Okay, so that will give me the formula without using any integration and all that. So I'll replace all this. So I'll get m1, which I'll now write as what? 16x. Okay, into y1, which is 4r1 by pi. I'll substitute r1 also later. But then plus m2, which is 20x. okay, into the unknown y coordinate y2 divided by m1 plus m2, which will give us 36x, the total mass. That should be what YCM. So YCM is 4r2 by 3 pi. Okay. So now you can cancel off the x and everything, and we can just see. I think 4x can be taken as a common term. Na? So 4 times 4r1 by 3 pi plus 5 times y2 divided by 9 is equal to 4r2 by 3 pi. So I should be getting y2 as 1 by 5 of 9r2 minus 4r1 into 4 by 3 pi. Just check my calculations. So I should be getting y2 as 4 by 15 pi into 9r2. So that is 9 into 6. Okay, minus 4r1, that is 4 into 4. This I should be getting in centimeters.
Yes.
So you have to be precise while writing the values, but it's not something very complicated because you're not really doing any integration and all that. Okay. So
30. 54 minus 16.
sorry,
54 minus 16.
sorry, yeah, 54. So 54 minus 16 will give us how much?
38.
So 4 by 15 pi into 38 centimeters. This is what the y coordinate will come out to be. So let's try and estimate this and see where exactly the center of mass is falling. So 4 multiplied by 38 divided by 15 divided by 3.142, let's say. So this is coming out to be 3.23 centimeters. It's actually falling, before the mass starts. Falling in that empty space, actually, the center of mass. So the center of mass is falling somewhere here. This is the center of mass of this mass, which I've taken M2 as. So this distance is about 3.23 centimeters, whereas this inner radius was 4 centimeters. This outer radius was 6 centimeters. So this is one way of doing this question. Okay. Now, actually, you can also do it by integration. There's nothing difficult in that also. You can slice rings, semi-rings, that is, of radius r and thickness dr, and do it just like the derivation we had done for the semi-disk. But the difference is that the limits will not be from 0 to capital R. The limits will be from
R1 to R2.
Okay. So you can try this question later when you're revising this by that sort of a method also.
So,
Yes.
so like, why are we saying that the YCM is equal to M1 Y1 plus M2 Y2 by M1 plus M2?
Okay, so see, this is where the superposition principle comes in. Okay, we are taking M in my diagram above, that the diagram right to the top left as the full semi-disk.
Yes, sir.
So the full semi-disk will get, if you place that M1 in the slot where you've cut out from M.
Yes, sir.
So M1 and M2 को अगर आप एक साथ place कर दोगे, so it covers the gap where you had cut out that semi-disk. So you get the full semi-disk M. Okay. So M is the superposition of M1 and M2. Got it now?
Yeah, sir, got it.
Okay, now you can replace M1 with a particle of its mass, where at its position of the center of mass at Y1.
Yes, sir.
And similarly, you can replace that, thick ring kind of thing M2 with another particle but of mass M2 at Y2.
Okay, sir, got it.
So the equivalent system, now you're reducing it to two particles at Y1 and Y2, M1 at Y1 and M2 at Y2. So their superposition will result in center of mass where at M1 Y1 plus M2 Y2 divided by M1 plus M2. No?
Okay, sir, got it.
So it's like a reduction method, that you have a body of certain mass and you know its center of mass. Now for the purpose of center of mass, you can replace that entire body with a particle of that total mass placed at its center of mass.
Yeah, sir. And so secondly, that M is equal to sigma pi R.
That is like sigma is like mass per unit area, na?
Yeah, sir.
So the total mass of the full semi-disk will be what? Sigma into area of the full semi-disk, no?
Yes, sir. Okay.
And like that, the semi-disk you're cutting out M1, that will be sigma into pi R1 square by 2. And that's why the remaining mass M2, which you get by slicing that part out, will be the difference of M1 M and M1.
Yes, sir. Yes.
Okay, so that principle is.
Okay, sir.
Done, sir.
Yeah. Okay, we will. So this is done.
Yes.
So
So
one
now, yeah. Now, people, I hope you have been doing revision of circular motion and work by energy and all properly for the test coming up.
Yes, sir.
Yeah. So tomorrow afternoon we have another session. Now, one thing I think I'll have to shift the session to 3:30 instead of 2:30. Is that okay with all of you?
Yes, sir.
Yes, sir.
Okay. So because I have to travel in between from one center to another, so I'll have to shift the session to 3:30 to 5:30 instead of, if everyone is okay with that. Right. And in tomorrow's session, we will do a little bit of revision of circular motion questions. And if you have any doubts, you can discuss that also. Okay.
Okay.
Yes, sir.
So if you have any doubts from the portion of the upcoming MT, ask those doubts in the beginning of the lecture only, so that I can structure the lecture such that I find time to discuss all the doubts. Okay.
Okay, sir.
Okay. So that's it for today's session, people. Wish you all the best.
Thank you.